Come on in. Step right up, step right up. Enjoy the time that is this physics class. That's my story. Anybody have any questions while we're waiting to start? We got about 2 minutes, 1 minute, somewhere around there. Careful, you all right, Johnny? All right. Well, it's getting about 5:20. Doesn't look like anybody had any chats or anything. Last time we finished chapter 26, so we're going into chapter 27 today. That's on magnetism, and we're going to start off talking about uh basically the Earth, the way that worked, and things like that. But before we do that, I want to review uh the cross product of two vectors, just not necessarily the calculational aspect, but the right hand rule associated with it, because in fact all of these right hand rules that we have in this branch of physics is basically due to cross products. So I thought I'd refresh your memory on what that is. So we only have five of you guys in here now, but it is time to start. So I'll tell you that basically originally there were these rocks that people discovered in what's modern day Greece, basically a place called Magnesia. Uh, in case I told anybody otherwise, at one time I thought Magnesia was on Anatolia, which is where Turkey is, but I was wrong about that. It's actually just across the water in Greece, uh, as best I can tell now. But anyways, those rocks were named magnets because they were rocks that were found in Magnesia. We now know those rocks are essentially rocks and minerals that contain large amounts of iron, and possibly, I guess, I don't know enough about geology, but possibly other ferromagnetic materials, maybe gadolinium or something like that. But anyways, these rocks did show what we call magnetism. So there was some aversion of one rock to another and some attraction of one rock to another. And that's where we got the origin of the phrase magnets, because these rocks are found in Magnesia, like I said, which is on the sort of southeast edge of Greece, just across the water, like I said, from Turkey. So what we've discovered since then is basically you can make magnets. One particularly good material is iron, and you can take iron, which is called ferromagnetic, and if it actually solidifies somewhat in a magnetic field, which obviously the Earth has, then there will be regions within the chunk of iron that we call neighborhoods. And those regions are regions where all of the atoms making up the iron essentially have their magnetic moments, which is basically a magnetic field that's created by their orbiting electrons cloud, if you will, but essentially have them all in one neighborhood, all aligned parallel. And in fact, they tend to align parallel to each other and specifically parallel to the existing magnetic field. Now, when you remove that magnetic field, assuming the iron's not molten or anything like that, then it tends to stay in that same orientation. And in fact, you can subject it to stronger and stronger magnetic fields and even larger fractions of the atoms align that way. But if you remove the magnetic field still stays as a result of how the molecules, or I keep wanting to say molecules, how the atoms align. So that's the nature of what we call ferromagnetic material. Now, there's another kind of material called paramagnetic, and paramagnetic material does the same thing. So if you take molten rock of a paramagnetic form or paramagnetic material, and you let it solidify in the existing magnetic field, then it will actually align parallel to that magnetic field, the little atoms and all that good stuff, and they make, make those little neighborhoods. In fact, they can somewhat align anyways, just by happenstance. But the main thing is when you remove them from the magnetic field, they essentially all fall back in line in random ways. So they're not necessarily going to have the neighborhoods existing anymore, whereas the ferromagnetic material tends to hold on to it unless you do things to actually make it go away. And then there's a third material called diamagnetic, and that actually aligns itself anti-parallel to the existing magnetic field. So if you have some rock solidify in an area where the magnetic field obviously points to the north, then these atoms in the diamagnetic material will actually align their magnetic fields pointing south. So it's kind of a weird thing, but they're like paramagnetism or paramagnetic materials in that generally when you remove the magnetic field, they somewhat go back to random. So those are the three major materials. Your book will talk much more about that, and I'll leave that reading up to you. There's always a lot of interesting facts and trivia type stuff, but also not just trivia stuff that helps you understand how the world works when you read these textbooks. So by all means, definitely read as much of your book as you can do. Again, like I said before, I recommend you read for as long as you can, which when you first start in college might be only 5 minutes at a time. So read 5 minutes at a time for about 10, 15 times, and then try 6 minutes, and then do that about 10 or 15 times, and then try 7 minutes. But anyways, just hopefully you can train yourself to do that. And hopefully by the end of your career, either in high school or your career in college or your career in whatever, you ultimately can read for 2 hours continuously without falling asleep, even if it's really something boring. So give that a try. And so I've given you an idea of where magnesia comes from, where the idea of magnetism comes from, why it was called magnetism. I've told you about the three types of materials. I'll tell you also that there's some concept called hysteresis, where you can't just know about iron and how it's going to behave just by knowing what conditions it's currently in. In fact, it remembers what conditions it's been in the past. So in that sense, it has this, what we call hysteresis effect. So just read that for your own edification and knowledge and good stuff like that. So I want to go ahead before we jump into the rest of this. I want to share my screen. I've been working trying to get something to help my students understand better how the right-hand rule works. And generally speaking, I always have to use two. I've got to use one that can be shown like this. Again, remember to use your right hand, not your left hand. But I either use it like that, or one thing I also do with my right-hand rule, which is the way I always learned it, was I pretend like this right here is one long axle. And that axle aligns itself along the first vector in the cross product. And then, of course, as long as you're aligned on that aligned along that first vector in the cross product, then all these positions are fair. What locks you down to a given position is such that you have to have your arm oriented such that the magnetic field, or in this case, the second vector of the cross product, can be curled towards with my fingers. So for instance, I want to be able to curl my fingers this way and have it point to the magnetic field. Or the second vector. And in this case, so the first vector would be that, and then the second vector would be that, and then the answer, the A cross B, would actually be in the direction of the thumb. So that's the two versions that are used, but I've noticed almost no students use this curling idea So I more or less just migrated to that. And then there's another one that I've always used for a current carrying wire. So for instance, if you happen to have a current carrying wire, what you're supposed to do is imagine that this is the current carrying wire, and let's say this pencil points in the direction that current flows. So you take your right hand, point your thumb in the direction that current flows, curl your fingers around, and then look at that. And the direction that your fingers curl around should indicate the direction of actual concentric circles around the wire. So one thing you need to notice is the concentric circles should be in a plane that's perpendicular to the current, and then it should be again in the correct direction according to your right hand rule. So for me, when I'm looking at this and the wire is carrying a current towards my forehead, then me looking back at the vector shows that the magnetic field would go around in a counterclockwise fashion. So the idea is you actually draw concentric circles. And when I say concentric, I mean the center coincides with the center of the wire. And I mean the axis of symmetry that the current's running down. So you put the center there, and then one radius would give you one magnetic field strength. If you go a little bigger, it's going to be a smaller magnetic field strength. A little bigger still, it's going to be smaller still, so on and so forth. And then everywhere along that line, the magnetic field points tangential to it. So those are the two right-hand rules. So I want to go ahead and share a screen and show you an attempt to help you better understand it. So let's start with share screen. Okay, it looks like it's sharing. So now I can turn mine on and tell it to share. Now it's starting. So hopefully you should see this in a second. Any minute now. All right, there it is. So this is a drawing of a human hand, right hand, obviously. And on that drawing of the human hand, I've also included a drawing of the A vector, the B vector, and then the C, which is equal to A cross B vector. So if you hold your hand like that, you can always say the first vector is your index finger, the second finger, which notice I've got it turned 90 degrees to the actual first finger, that should be the second finger. And then the thumb, which is 90 degrees to both, should point in the direction of A cross B. That also is shown by the A red vector, B blue vector, with the two vectors tail to tail. And it takes 3 points to define a plane. So all you need is the tail where both A and B coincide. That's 1 point. The end of A is another point. The end of B is another point. So you've already defined a plane just with those 3 points. And what I'm saying is if you complete that parallelogram, then it turns out that when you do the A cross B, the cross product of A and B, the magnitude of that vector will be, in fact, equal to the area of that parallelogram. But the direction of that vector will be given by a vector that's mutually perpendicular to A, to B. And of course, that means it also has to have one of 2 choices. In this case, you could see it point up or it could point down. But the right-hand rule, again, says first vector's in the A direction, second vector's in the B direction, and then C is given by your thumb. So hopefully that'll help you over and over and over again. If you're curious why it's the area of the parallelogram, just remember that A sine theta would give you the component of A that's actually perpendicular to vector B. So in a parallelogram, remember it's sort of like a triangle in that you take one side and you're going to multiply that by a dimension perpendicular to it. So if you take B and then multiply it by the component of A perpendicular to it, then you'll actually get the area of the parallelogram. So that's what AB sine theta ends up giving you, because A sine theta is the perpendicular component and then B is the vector itself. Of course, you could also reverse it all and then say B sine theta is the component of B perpendicular to A, and then the parallelogram is A times B sine theta. Works the same either way. So any questions on that? All right, so that's a classic example of how the cross product is supposed to work out. And when you know that cross product and you know what vectors are involved, then you can quickly use the right-hand rule just by, again, saying your first vector is your index finger, your second vector, which is perpendicular to your index finger, is your second vector, and that's your middle finger. And then, of course, C is mutually perpendicular to both of them, and that is A cross B. So any questions on that? All right, so now that we have that, what I want to tell you is that the Earth, in fact, does have a magnetic field. So if you were to look at the Earth like this, say, yeah, I just drew a magically perfect circle. So sorry, I still have to enjoy that a little bit. Just technology for old people, you know. So this is Earth. And if you actually imagine, say, that this is the actual North Pole and this is the actual South Pole of the Earth. And let's say you had, for instance, the United States, there's Texas, there's the Gulf of Mexico, there's Florida, coming a little closer to the equator than I had originally drawn it, so it should actually be a little closer. And then, of course, this is Maine and stuff up here. And then you have Canada, and you have the Great Lakes around in this area like this. But up here, there's, you know, a huge body of water in Canada. And somewhere around there, roughly, is actually the magnetic field, the quote unquote North Pole of the magnetic field of the Earth, which is a really, really odd little misnomer. So if you wanted to actually picture it, what you'd have to picture is, let's take a bar magnet, and let's in fact imagine the bar magnet is inside of the Earth like this, and this is going to the backside of the Earth, of course. So it's also fairly close to the South Pole. This end back here is, and actually I need to go like that. Okay, and then this other part of the vector or of the magnet is right there. But here's the weird part. Notice the letter right there is S, not N, because it turns out the north magnetic pole, since the north end of a compass points towards it, has to be technically a south pole. So that is actually a pretty good rendition of a bar magnet. And in fact, if you look at the magnetic field from a bar magnet, the Earth's magnetic field is pretty comparable. What we see is, let me do a different color for the magnetic field lines. What we see is, and I apologize if this mnemonic seems a little bit offensive. I don't mean it to be that way. It just happens to be useful. And that is that magnetic field lines, are sort of like elderly people in that they leave the north and go into the south. So you can imagine the magnetic field lines coming out of the North Pole, which is way down here, arcing back this way, and then coming back in the South Pole like this. So that's the actual direction of the magnetic field, all and those points along that arc. Now there's another magnetic field line, of course, that goes right through here. And notice they're continuous loops. That's sort of the nature of the magnetic field, is the loops are always complete loops. They don't stop and start. But if you remember how we handled our electric fields, we sort of imagined the electric fields as starting on a positive charge and then ending on a negative charge. So that was the direction they went. But they literally would stop at a negative charge and they'd start up at a positive charge. In this case, they never stop. They just go completely through the south end of the magnet and the north end of the magnet and that sort of stuff. So that's one of the differences. And it turns out that if you were to take one of these magnets and cut it in half, it wouldn't get a South Pole and a North Pole left over. In fact, you'd get a North Pole, South Pole on one half and a North Pole, South Pole on another half. And if you keep doing that over and over and over again, you'll get smaller and smaller complete magnets until basically you've cut into a neighborhood that's too small to really have an appreciable magnetic field. But you're never going to get an isolated North Pole or an isolated South Pole. So that's actually somewhat how the magnetic field behaves. I think your book talks about the angle of dip or whatever, which is basically how much the magnetic field dips below horizontal and stuff like that. But the main thing is to remember that with a magnet, whether it be a bar magnet or otherwise, you're always going to have a North Pole and a South Pole. And the magnetic field lines, as I said, are continuous loops, and they exit the North Pole and they enter the South Pole like this. So now I can write north over again, and I can write south over again. And I didn't really mean these lines to be this thick, so I'll try to correct that now. So this magnetic field line will go like this, say, and of course I'm running a little bit out of space here, so it's not quite as realistic as it should be. So I apologize for that, but that's part of what you need to know. So honestly, we don't exactly know all the details of why the Earth has a magnetic field. We have some sense of it. I can do some sort of hand wavy things like tell you that Maxwell's equations tell us that whenever a charged particle accelerates, it creates electromagnetic radiation. And electromagnetic radiation is quite a bit different from just a magnetic field. Electromagnetic radiation is normally something like an electric field oscillating in one plane. So it goes, points up. It's very, very weak initially, but pointing up, and then it gets stronger, 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 reaches its max strength, and then starts to weaken, 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 still pointing up until it becomes zero. And then it starts pointing down and is weak, and then stronger and stronger and stronger until it gets to the strongest, and then it starts to weaken again, but still going down and weaker and weaker and weaker. When it gets to zero, it starts again to the upside, and then perpendicular to that is the magnetic field, which would be like this, and it does the same thing, and it's in phase. So when the electric field is the weakest or down to zero, for instance, the magnetic field is also down to zero. And the electric field and the magnetic field travel in a direction. In other words, the electromagnetic radiation travels in a direction given by E cross B. So if you make E the electric field, which I show you guys as if it were vertical, and B the magnetic field as my second finger, then my thumb points in the direction that the actual wave will propagate. That's what electromagnetic radiation is. So that's quite a bit different from just a static magnetic field sitting there due to iron or nickel or gadolinium or whatever. So we don't necessarily know, but some of the things we do know are that one, we know that the planets and bodies in our solar system radiate heat in a rate that's proportional to basically the area, the surface area. And of course, the surface area of a sphere is 4 pi r squared. So that means that the amount of time required for the inside of the planet to cool off is directly proportional to the square of the radius. So if you double the radius, it's going to maybe last 4 times as long. If you quadruple the radius, it's going to last 16 times as long. But the amount of heat that's put into the planet initially is directly proportional to the volume. And the volume for a sphere is 4/3 pi r cubed. So it turns out that the ability of a body to still have heat inside of it is directly proportional to R, because you can basically take 4 pi or 4/3 pi r cubed and divide it by 4 pi r squared and just get R. And what that means is if I double the radius of a planet, I'm twice as likely to still have heat inside the planet. If I go to 4 times, I'm 4 times as likely to still have heat inside. Well, heat, for starters, it comes from radioactive decay. It calls from gravitational infalling. It calls from just basically the pressure and temperature laws deep inside the planet. But initially, it's largely radioactive decay of uranium and things like that inside the Earth. So if you think about it that way, then that heat can do stuff. It can actually make part of the core molten. And in fact, we know that our Earth has a molten core and it surrounds a solid core. So what we've discovered is we think that planets with a molten core, or planets with enough heat to have a molten core, can have a magnetic field. But in the idea of the hand waving thing that I was saying, where the charged particles have to accelerate, well, if the core is molten, then there's some probability, some higher probability that high of a temperature would compel a lot of the atoms and molecules in the molten core to be ionized as opposed to just neutral. So now you've got charged particles. Now, how do you get them accelerating? Well, the rotation of the Earth would be an acceleration. But again, that's still that hand waving thing where I'm talking about accelerating particles, charged particles, creating electromagnetic radiation, which again is something different in the magnetic field. But here's the neat part about it. So we have the idea that obviously if the planet still has a molten core and rotates, we should be able to find magnetic fields. So if we look at the Earth, which is about a fourth of the radius or excuse me, if we look at the moon, which is about a fourth of the radius of the Earth, it's about 4 times less likely to still have heat. And as best we can tell, it doesn't have really much internal heat. There's no plate tectonics. There's no volcanism, no continental drift, any of that kind of stuff. No lobate scarps or anything like that. That would be indicative of a recent event. So we think the moon, being a quarter of the side of the Earth, is going to be cooled off and have essentially no or very little heat left in it, and definitely not a molten core. Pluto is about the same size, in fact, a little smaller. Mercury's a little bigger, and as best we can tell, Mercury's about dead and it has no magnetic field. Venus is really kind of cool because Venus is about 94% the radius of the Earth. So based on the radius idea, it should have about as much, about 94% as much internal heat as the Earth does. And it does. As best we can tell, we think it probably does have a molten core, maybe even a molten outer core, and then a solid inner core. I'm not a planetary astronomer, so I don't know that off the top of my head, but we might actually know that now. But here's the thing, it has almost no magnetic field. But what we do know is early, or what we do believe is early in the formation of our solar system, Venus probably shortly after it solidified, maybe within the first billion years or so after the solar system formed, something seems to have hit Venus so hard that it actually caused it to rotate in the opposite direction than it normally had. So basically all the planets revolve in one direction as seen from above, and then they rotate about their own axes in that same direction. And that's what our computer models say you expect if the nebular hypothesis is really the true way that our solar system was formed. So the planets in general revolve and rotate in the same sense. Venus, on the other hand, does not do that. It revolves but rotates in an opposite direction. So and it does so very slowly. In fact, it does so slowly that a day is longer than a year on Venus. So it literally takes more time for Venus to do one rotation than it does for Venus to do one revolution. And because of that slow speed, we think that's the reason that it has very little magnetic field. There are some very magnetic areas, for instance, Io. Last I checked, Io was the most volcanically active place that we've ever found in the universe. It is quite a bit bigger than our moon, but still not necessarily big enough to have a lot of internal heat. But what we discovered is basically it's in a synchronous orbit with two of the other moons of Jupiter. And basically what you get is Jupiter pulling it from one direction and a big moon pulling it from the opposite direction, causing it to stretch this way. And then sometime later, those same two moon, or that same moon and planet, is going to stretch that same moon this way. So it's doing this, this. And as best we can tell, calculations have been done, and it seems like that's about the amount of energy we would need for it to have as many volcanoes as we see. So yeah, Io really, if you look at a picture of the surface of Io, it really does look as close to hell as possible. It's sort of a sulfury looking deathscape, if you will. I don't think we've ever flown by it and taken a picture that there wasn't at least one volcano going off. So anyways, that's some of the stuff about the magnetic fields that we find, and different ways we could have heat inside of the planet, so on and so forth. Io, I think the last I checked, Io does have a magnetic field, but now we know a little bit about that. Now, what we need to know is what are the ramifications? So it turns out that one thing we know for sure is just about every type of magnetism we find, we can associate it with what we know from Maxwell's equations, or basically we can find some kind of current going in a circle. So current going in a circle, remember current is a certain number of coulombs, charge in other words, per second. So if you think about an electron, it has a charge of 1.602 times 10 to the negative 19th coulombs. But if it also has a velocity, if you imagine it literally like a particle orbiting around the nucleus, for instance, then there's not a whole lot of difference between that electron orbiting around a circle than there is a current going around in a circle. And as best we can tell, that does create a magnetic moment, which we're going to calculate later, and therefore it creates a magnetic field. So we sort of lean towards the idea that these electrons in orbit around nuclei in various atoms and molecules can actually create magnetic fields associated with the atoms and molecules. And again, if they align in those little neighborhoods, then you start getting the phenomena of magnetism, as long as you have enough of them. So we'll learn a little bit about that, but we'll also learn that currents create magnetic fields. So we found several ways that magnetism can be created. And now I'm going to go ahead and give you some of the results of it so we can do some simple calculations. So it turns out if you have a current carrying wire, so let's imagine a current, actually I want to draw this in the middle. Let me undo that. I'm going to draw this current in the middle so we can really get a good vision. Whoa, that was just horrible. I don't know what happened there. So I'm trying to cheat and use the program that actually corrects everything. Let's imagine that this is in fact a very, very long current carrying wire. And here's the other side of the very, very long current carrying wire. And what we're going to do is we're going to imagine that there is a current coming out of it. And let's say this current is going to be this direction right here. We'll say that's the current I. Okay. Well, it turns out this is the right-hand rule that I told you I haven't been able to get rid of. I'm going to give y'all a way of doing it without this one tonight, but I'm not sure it'll stick. If it doesn't, that's okay. It's just something I'm trying. But if you take this wire again and you point, in this case, I'm pointing my pencil in the direction of up, which is the current direction current's going, then I'll lay my thumb along that current carrying wire, and my thumb is pointing in the direction of the current. My fingers curl around the wire. And what you really need to think of is not so much fingers, because that's got little straight parts and then a bend and then a straight part and then a bend. Think more along the lines of cooked spaghetti noodles going around it, because what you want to do is you want to think, let's take the smallest length of spaghetti noodle that we can completely wrap around this wire. And that is the center axis of that spaghetti noodle. When you do that is exactly a line of magnetism. So if you take any vector that's parallel to any part of that line that represents the center of the spaghetti noodle, then a vector tangential to that will be exactly the direction that the magnetic field points at that specific position. So we can take this and say, let's imagine, for instance, a magnetic field around it as a spaghetti noodle. If I did that, then what I'm saying is you could take the spaghetti noodle and write it right here, and that's a darker color blue. And then over here, I'm going to try to make an identical one. That's the spaghetti noodle again on the other side. And of course, the spaghetti noodle would come out of the page and curve back around like that, and then come out of the page on the other side of the spaghetti noodle and come around like that. Now, if you went around the back, you would see that that spaghetti noodle continues to go around the back and comes back out this way. And specifically, according to our right-hand rule, that should actually go, or that should actually point in the direction of the magnetic field. So in this case, we're imagining the magnetic field sticking out of the page on this side, because remember, I'm saying I grab it with my right hand. So if I look down from above, the fingers are curling around in a counterclockwise direction. So that means if I go to the left of the wire, look to the left of the wire as I'm looking down, then it's coming out of the page. And then if I look to the right of the wire, then it's going into the page. And then out here in front of the wire, it's going to the right, and back here in the back of the wire, it is going to the left. Okay. And in fact, it's tangential everywhere. So you could say, for instance, right here, maybe it goes that way. Right here, maybe it goes that way, so on and so forth. So that's really what the magnetic field direction is supposed to be. As I told you, you could actually imagine concentric circles around it, and that would be more or less perfect. So let's give that a try. Let's imagine drawing a concentric circle completely around it. Okay, so that's supposed to be a concentric circle. I've actually got it tilted. That's kind of screwed up. And I got it off center, which is kind of screwed up. I wish I could tilt it, but it won't let me. So I want to redraw that, throw that sucker away. Try again. Like that. That looks a little better. It's not centered, but at least now I can center it. So if we're looking at this, what I'm imagining, ooh, I didn't want that. I still want it to be about that angle. So I'm going to zoom in a little bit specifically so I can edit it to show you what's going on here. So since this is back behind it, and I need you to understand that it's back behind it, I'm going to take the eraser and just do like that. Oops. And just do the eraser again over this side like that. And now I'm going to take my pen and fill that back in, just this part, because I didn't really want to break that. And what I could also do is make this just a little bit bigger, so it will then look like a dash line, because I'm just going to erase parts of it like that. Okay, so again, as I'm saying, right here to the right of the wire, the magnetic field should in fact point into the page. And right here, it should point out of the page. Okay. And then, like I said, directly in front, I'm not trying, if I wanted to try to represent this three-dimensional, I'd go a little bit right of center or a little bit left of center to show it. But I'm just trying to say this is directly in front, and therefore the magnetic field points to the right there, and right back here, it points to the left. Right here, it points that way. Right here, it points that way. Right here, it points that way. Notice how it's just tangential to the circle at each point. So that's basically it. So does everybody understand how the actual direction of the magnetic field as a result of the existing current is? That's sort of the key, is making some sense about what the directions of the current carrying wire, what direction it makes a magnetic field point in. So this didn't turn out too good. I want to kill that. But the main thing is you do get this idea that a spaghetti noodle would clearly come out of the page on one side and into the page on the other. So hopefully that alone should be able to help you. Anybody have any questions on that? Okay. This is supposed to be a circle, which it used to be, and it's no longer. So this is great. But anyways, good enough. And then, like I said, over this side, it's coming out of the page. So I'm going to try to do, oh, that's just horrible. That was horrible too. But let's try. Oh, that's a terrible circle, but we're going to take it. All right, so that's what the magnetic field should look like. And I will also tell you, we'll derive this later, but the magnetic field, let's say at this particular point, right? Oh, I hate when it does that. Let's say the magnetic field at this particular point, which happens to be a distance r from the center, that magnetic field right there is B is equal to mu 0 times I over 2 pi times r, and that's the magnitude. And as you can tell, these tangential lines give the actual direction. I should tell you that for starters, the magnetic field has dimensions of what we call a Tesla, and it's also Weber per meter squared. But right now it's a Tesla. I will tell you another unit for the magnetic field is the Gauss, and that is given such that 1 Gauss is equal to about 1 times 10 to the negative 4th Tesla. So it's very, very weak. And in fact, the magnetic field of the Earth is about 0.5 times 10 to the negative 4th Tesla, which is about 0.5 Gauss. Okay, so that's the magnetic field of the Earth. I should also tell you this little constant mu 0 is called the permeability. They often say it like this. Oops. They often say the permeability of free space, which they mean basically a vacuum. Okay. And it's given by mu 0 equals 4 pi times 10 to the negative 7th Tesla meters per amp. So these are all very important quantities. That's the constant. This is the equation for the magnetic field. This is what the mu 0 is called. And 1 Gauss is equal to 10 to the negative 4th Tesla is also important. Anybody have any questions on that part? Okay. So in addition to that, I will tell you that you can also find this direction with a right-hand rule as well. It turns out that you can imagine a vector I times L. So let's say, remember, I is the current, and L would be the length of the wire, or some little small part of it you could call I times DL. That would work as well. So if you call this vector IL, then you also could use another vector pointing, for instance, to a place in space where you wish to know the magnetic field. So from that current carrying wire to a point in space right here, which is R, okay, that's the distance away. Now, if you actually do that, then you can realize that B is essentially parallel to IL cross the R vector that I just showed you. Okay. So if you look at where that vector is pointing, it's pointing to this spot right here. Okay. And that R vector is supposed to point from the tail of the IL vector to the point at which you wish to know the magnetic field. So this is point, oops. This is the point at which you wish to know the direction of the B field. And notice it points from the tail of the I vector. So points from tail of IL vector to point in space. So again, using our right-hand rule that I showed you before, there is a way where you don't have to grab the wire like I had told you before, where I was saying do like this. In fact, you can still use this, where this is your first vector, this is your second vector, and this is the cross product. So what you have to do is you put your finger in the direction of the current along the wire. So it would be up in this particular drawing. And then you adjust your hand so that your middle finger points from that current to where you wish to know the magnetic field. So if I put it over here to the right of the wire, my right, you guys are looking at it probably as your left, then it goes into the board according to my thumb. And that's exactly what's happening here. Is you see that this magnetic field, actually let's do that with the automatic drawing correct on. That is, oh, okay, that went badly. So that is actually the direction of the magnetic field there. But notice also, if you chose to pick the point back behind the wire, then all you have to do is take and move your second finger, your middle finger, to point backwards. And then you see right back there in the back, your middle finger is pointing to back behind the wire, but my thumb is pointing to the left, which is exactly the direction that our diagram shows. If you want to go to the right, then you turn it this way, and you see that this middle finger is pointing from the wire to a point on the what we call the left-hand side of the wire, what I'm calling left-hand side because I'm looking at it. And there, my thumb is pointing out, so you see that my thumb is actually in the correct direction for the magnetic field. And then finally, right in front of me, I could have the middle finger pointing out towards me. The IL, the first finger, is actually going in the direction of IL. The R vector that points to me is my middle finger pointing at me, and my finger is pointing to the right. So that says the magnetic field should point to the right. So that's another way you can do it. Hopefully between that and this, you can get it. Okay. Any questions on that? All right, so now that we have that, and I told you the formula for that, then we can also figure out some formulas. So I'm basically giving you the formulas that you'll be needing. And that means by explaining these concepts right now, you can go ahead and start applying the equations like the examples in the book and start doing your homework. So that's what I'm trying to do here. So let's imagine now that we have a wire. Here's one wire. I actually wanted that to be a separate line, not to connect them. Okay, that's one wire. And let's say some distance away over here is another wire. Okay, now let's say in this case, I've got a current going up, and that's going to be I1. And let's say I also have a current going down, and that one's going to be called I2. And let's say that the distance between these two wires is a distance D. Okay. What I would like to know is what, if any, force there is on wire 1 as a result of wire 2. Well, there turns out to be an equation that gives us that. So first off, I would like to give you one of those equations. There's a couple ways you can do it. So one of the equations is there exists a small amount of force dF equal to I dl vector crossed with a B vector. So that is actually one formula. And of course, if you have a uniform magnetic field and a straight wire, then this ultimately just reduces to, let's say, for uniform B field and a straight wire, we end up getting F. Well, let's do the magnitude. So I'll just say F is equal to Bill sine theta. And I like doing Bill because obviously my first name is Billy. But really it's not the most convenient way. It really should be like ILB or something like that, or LIB. Any of those would work, because really you want to think in terms of that cross product so you can get an idea of the actual direction. So also, that helps you understand exactly what the angle theta is. As you see, the sine theta is exactly like the sine theta we had from the cross product. So what this means is if you had, for instance, the vector IDL, and you had with that a vector B, then you put those two vectors tail to tail, and the angle between them there is the theta that we were talking about. And of course, like we said before, that also means the C is equal to, well, I'll just say IDL cross B is what that is. Okay, so let's do this. I would like to know the F. I'm going to use black here. I would like to know the force on 2 as a result of 1. No, actually, I want to do the other way around. Let's do the force on 1 as a result of 2. So this is equal to the force on wire 1 due to the magnetic field of wire 2. Okay, so we have current I2 going downward. Can anybody tell me, using your right hand rule, exactly which direction should the magnetic field be pointing? And let's say at this point right here. Anybody tell me what direction? And now completely forget about I1 right now. We just want to talk about I2. So can somebody tell me, this is that dot supposed to be in the same plane as the wire, okay? And I want to know in what direction is the magnetic field pointing there. Answers could be up, down, right, left, into the page, out of the page.
To the right.
Okay. So thank you for answering. There's two ways we can do it. The one that I thought is the easiest, and I hadn't introduced until tonight, or excuse me, and I had introduced long before tonight, is the one where you grab the wire with your right hand and you have your thumb pointing in the direction of the current. So what we're looking at right now is the wire on the right, which has the current I2 going down. So that means I need to take my right hand and point my thumb down. Okay. Now I'll wrap my fingers around it this way. And if I look from above, that means it's going clockwise as seen from above. So if I look from up there where it says www.youtube.com, if my eyeball is up there looking downward along the page, then I would see the circle around the wire traversing in a clockwise direction. So now, does anybody have an idea which direction the magnetic field would point? And I'm not necessarily saying he's wrong or right, but does anybody have an idea which direction the magnetic field would point at that dot, again, which is in the same plane as the wire? All right, here's another way. Remember, you can stick your index finger in the direction of I times L, which would be down. And then you can take your middle finger and point that from the center of the current carrying wire, and meaning the symmetry axis of it, from that to the point at which you wish to know the magnetic field, right? So I want to know the magnetic field over there on that side. So that means my hand has to be like this with my middle finger pointing to that side over there. And then my thumb points in the direction of the magnetic field. Can everybody see which direction my thumb is pointing now? So we got middle finger, index finger going down, middle finger going to my right, you guys is left, and then the thumb is pointing towards me. So what do y'all think the answer is now for the magnetic field direction at that dot? All right, I don't want to cause any undue stress. I'm going to draw a circle right here. And that circle is going to represent the magnetic field direction at that particular point. I'm also going to move the circle up a little bit. So actually, I guess I'm just going to shrink it for some reason, because I didn't mean to do that either. Nope, not letting me do it that way. Oh, okay, I'll do that. And now what I'm going to do is take it off the automatic draw and say, ooh. In that case, we now have exactly the direction it should be coming out of the page. Okay. If you do the same thing with the side over where the wire is, then we'll draw yet another circle. And this circle, crap, of course I didn't have it on auto draw. That circle would actually have the magnetic field pointing into the board. So right here, the magnetic field points into the board, and that's where the current I1 is. So the magnetic field B is actually pointing into the page at I1. So we know the direction should be given by I dl cross B. So what that means is I'm going to take my index finger and point it in the direction of the first vector, which is I dl. So that means up, because that's which way the current's going. And then I'm going to take my middle finger and I'm going to point it in the direction of the magnetic field, which is into the board. And you see that now my thumb of my right hand is pointing to the left. So that tells us the actual force would be this way. That's the force F2, or excuse me, F12, which is the force on 1 due to 2. Now, what is the actual formula for that? In other words, what's the magnitude? Well, the magnitude of F12 is actually equal to, since this is going to be a uniform magnetic field because the two wires are equally long, we know that the magnetic field is going to be mu0, and then the magnetic field is being caused by current I2, so it'd be mu0 over times I2, and then all that'll be divided by 2 pi times the distance between the wires, because that's what gauges on how strong the magnetic field is at the wire. So now I've got B. Now I need I, the current of the wire that's being affected. So in this case, that means I1 now. And then I have to multiply that by the length of the wire, which would be length 1. Okay. So on this diagram, for instance, we might say that this is L1 down to here. Okay. Often what happens is we are often asked to calculate, instead of F12, we'd be asked to calculate the force per unit length of F12. So that would be the force divided by L1, which would be mu 0 I2 I1 over 2 pi d. So these are also two helpful equations. And that is the force on two parallel wires. Now, notice these two wires are have currents going anti-parallel. So what we just learned is that anti-parallel, which means 180 degrees from each other, anti-parallel currents repel. And if you worked out the same problem for I2 going up, then your right-hand rule would say the current I2 going up would create a magnetic field at I1 that points out of the board. And then you'd say, of course, IDL cross B, and you see the wire, the force would actually point towards the other wire. So we also see that parallel currents attract. So I know I'm leaving off sort of a key word there, but I'm saying repel each other and attract each other, or repel one another and attract one another. So those are two neat little findings we've had here. In fact, this equation right here we'll use next time, because I have a fun little problem that we're going to use some calculus for, to calculate the force on a basically I think it was a glass window or something like that. So anyways, anybody have any questions on that force? And by the way, this does reduce to this, provided all this stuff is true. Okay. Now we've got about 20 more minutes, and there's another equation that comes in really handy. And this is the force on a current carrying particle. Or excuse me, I don't know why I said that. The force on a charged particle moving with velocity v. So it turns out that the force that a particle of charge q feels when it has a velocity v is qv cross b. Okay, so this is the charge of the particle. This is the velocity of the particle. And this is the magnetic field strength. Which you could also just call the magnetic field. So I'll just put it there, because really it's a vector quantity. So you're doing a cross product. So you really actually need the vector. But anyways, that's QV cross B. So that's another equation. And in fact, if you want to take into account all the things that could cause a charge Q to accelerate, then you'd have to add a term for the electric field, and you get the force on a charged particle is equal to Q times the electric field plus Q times V cross B. And this is called the Lorentz force law. So that would be the total deal. So if you imagine, for instance, there used to be a time, believe it or not, when your car could listen to the radio because of something very odd. There was a big long piece of metal that stuck out of your hood of your car, or out by your trunk, or something weird like that, and it was called an antenna. So let me show you what that would look like. So imagine this is an antenna, and the antenna is made of a conductor. So In fact, it would look like that. It'd have that little button on the top or whatever. Now, if you imagine electromagnetic radiation, like I just finished telling you about, what we have is, let's imagine, I'm going to do a different color for this. Hold on a second. Let's imagine the electric field is coming from back there. Now, I'm going to say the electric field is polarized vertically. Actually, I don't like that one. The electric field is polarized vertically, and therefore it looks like this. This part right here means the electric field is very strong and pointing upward. This means it's less strong and pointing upward. This means it's less strong and pointing upward. This means it's less strong again, but now pointing downward. Very strong and pointing downward. Actually, that's bad. Both of those were terrible. They're all supposed to be vertical. So actually, I hate all that. Sometimes my perfectionism really gets the best of me. So it's that way, it's that way, it's that way, it's that way, and that way. So that's the electric field. And then over here would be the magnetic field. And notice how I drew them sort of in phase, or I tried to show that they were in fact in phase. And this magnetic field should actually come all the way to here. That. And then, of course, we got the magnetic field here is actually in front. And, of course, I drew that crooked. This one's like that, and then this one's like that. Okay, so that's actually what the magnetic field looks like, and I should be a little careful here. I want to make sure y'all see that's behind the electric field, so you know that it's actually pointing sort of to the left. Okay, so that's the magnetic field, and notice that E cross B does give you the velocity of the electromagnetic radiation, which would be right here. Okay, so notice what's going to happen. You've got all these little free charges inside of this conductor. So let me show you what they look like. We've got basically, you know, they're electrons, so we'll go ahead and put little positive symbols in there like that. And they're just free to move because it's a conductor. So when the electric field gets there and the magnetic field gets there, the magnetic field can't do anything because the magnetic field requires the particles to have a velocity. And right now I'm just drawing them as if they're sitting still. They're wobbling and stuff like that. So they can do a little bit, but they're basically wobbling in random directions. So the random force is in random directions, which means it makes no net effect. But once the electric field, which is co-aligned, by the way, with the magnetic field, once the electric field is hitting the charged particle, these particles, I did this today too. I was talking about electrons and I drew them as positive particles. That's okay. We'll just remember it's conventional current. So that's the direction that conventional current should go, is the direction that positive charges go. So in this case, you can imagine that positive charges are going up when the electric field hits them, because that's what electric fields point in. They point in the direction that positive charges go. So what's going to happen is you're going to get the electric field pointing upward, and the charged particle, which has a charge of positive, initially has a V equals 0, and it also has a magnetic field pointing this way. So this is the initial, this is the initial state of the positive particle. Now, as soon as that electric field starts hitting it, what we see is then this positive particle is going to start going up with a velocity v. But now you can see that QV points up and B points to the left. So now the particle actually feels a force pointing out of the page. So all of a sudden there is a force due to B pointing out of the page. Okay, so that's going to tend to make the positive particle go up as a result of the electric field, and then the magnetic field kicks in. It's going to start making it turn towards us. And then when you see the velocities going towards us a little bit, and you do QV cross B, it points perpendicular to the velocity again, and then perpendicular again, and then perpendicular again. So what you ultimately get is that the positive particle is going to essentially do this. I'll try to draw it. Let's see. I'll draw it with this green path. It's going to start here and go up in a circle and then back that way like that. So out here, it's going to be going down. Up there, it's going to be coming this way, and so on and so forth. So that's what it's going to do. It's going to go woo, woo, woo. If the magnetic field came in a different way and the electric field came in a different way, then there'd be a whole different motion. But that's the main thing, is you'd see that it's going to cause the electric field, at least while the electric field is pointing up, that's going to cause the particle to start going up. And then the magnetic field is going to kick in, and that's going to cause it to start going perpendicular to itself, which means it's going to try to make a circle, and it's going to go like that. But if that circle can complete itself before we get to the negative, then that's what's going to happen. However, once we get to the electric field being zero, if it sinks so that the positive particle was back where it started from when the electric field hit zero, now the electric field is going to make it accelerate downward. And then that's going to cause the magnetic field to make it go into the board. And it's going to make a loop that way. So the next phase would be, and I'll draw this with a different color. Let's draw this one with a red color. So the next part of it would cause the particle to go like this. And I'm drawing these as ovals, not because they're not circles, but because I'm trying to show that they're actual circles, but in 3 dimensions, so that we're only seeing the side of them. So that's pretty much what's going to happen. It's going to go this way, and then it's going to go that way, right? So anyways, that's a nice little exercise for you guys to try to use your right hand rules to figure out stuff. I would highly recommend you going through the end of the chapter of your book in chapter 27 and look for all the little pictures it has where it has velocity or magnetic field or current, and see if you can use your right hand rule to correctly get the right answers. Remember, all the odds are in the back of the book. If you want to try any of the evens, you just can text me and say, hey, what's the answer to number 20 of chapter 27? In Giancole's book, and just make sure you text me and tell me you're in 242, because 202 is also Giancole, but it's a different book. So if you do that, then I can immediately tell you what the right answer is, either by checking it, or I can pull out the solutions manual if I don't have the problem with me. So make sure you do that. We do have a final. We've got about 10 minutes left. We do have a final. We have a second midterm that's supposed to occur on your next lab meeting. And you guys meet on Tuesdays and Thursdays. So I think your next lab meeting is Tuesday after class. Is that correct? I think so.
Yes.
Okay, that's cool. So you do expect, or you should expect, that to occur. And what you can do is, like I said, the practice test is up there. Take it as many times as you can. Just because I did move it back to help everybody, but I want to be as helpful as possible. So I'll make sure I try to pay close attention to my text messages over the weekend. So if you are working a problem and you don't really understand it, take a photograph of it, including the answers as well as the full question. I can zoom in on the photo to see it, and I can help you with it. So, and the more you tell me about what you don't understand, the better I can help you, because I don't want to just give you the answer. What I'd rather do is tell you enough that you can figure out the answer. So the more information you give me, which includes like the whole question, all the answer choices because they're multiple choice, and then also exactly what you think you're having problems with. If you don't really know anything, you can't get started at all, just say, I really don't have any idea even how to start this, then I will address that as well. It's not a problem of me not wanting to give you the right answer. It's just a matter of me wanting to give you the minimal answer I can to help you. So feel free to do that. Anybody have any questions on these things? So something neat that comes from this, which I can show you now because we got about 8 minutes left. I've shown you all the equations that we have. So you can imagine, for instance, if we had, let's say we have a negative particle this time. So it's like an electron or something. And actually, I really hate this not automatically making my circles. Okay, so this is going to be a negative particle. And in fact, its velocity is going to be this way. And then I'm going to say it's going into a magnetic field, which I'll mark with green. And the magnetic fields are going to be pointing into the board or into the screen like this. And it's a uniform magnetic field, which that last circle does not give you that impression. Neither does this oval. That's making me mad. Okay, good enough. Okay, I'm going to erase you. I don't know how. Oh, well. Close enough. Okay. Okay, we'll leave that. Go away, ball. Okay, so anyways, let's say all of these are pointing into the page. That means you draw it like this because it looks like the back of an arrow, you know, the little feathers that are on the arrow, like in a bow and arrow. So that's what we're doing. Actually, I do now get rid of this. And now I'm going to put the circle back on and do this and then take this special drawing like that. So as I do this, notice there's no force on the electron until it gets into the magnetic field. Once it gets into the magnetic field, then V is pointing to the right, but notice QV would be a vector that points this way. That's the vector QV because the Q is negative. So remember that when you multiply a scalar times a vector, it doesn't change the direction of the vector unless the scalar is negative. In that case, it changes it by 180 degrees. Otherwise, it only changes the size. So if the number is bigger than 1, it makes it longer. If the number is smaller than 1, it makes it shorter, that kind of thing. So now we've got QV, and then I need my right-hand rule. Here it is. QV is the first vector. Remember, the equation that we're working it with is F is equal to QV cross B. So QV points to the left. That means I'm going to point my index finger to the left. I'm going to make sure my middle finger is perpendicular to it. Now I've got to turn my hand upside down so that my middle finger points into the page. And I see that the force will actually be downward. So when the charged particle gets right here, actually, I shouldn't do that. I should do it in blue. And I should do my circle again. So when it gets right here, it's still a negative particle, but now the force is this way. Well, that's going to cause it to accelerate in the downward direction. So the particle might now be here. Again, it's negative, but now the force is pointing perpendicular to the velocity again. So, oops. And get rid of that. Okay, so now the velocity is pointing this way. So again, the force is this way. And then the particle moves, say, to here. Again, it's negatively charged. Now the velocity is actually going downward and the QV is actually going upward. So now the force is this way. So what you see is when this particle goes into the electric field, the path it's going to follow is something like this. And if the magnetic field is uniform enough and big enough, then it should complete a circle. We know, according to Newton's second law, that the net force acting on a system is equal to the mass of the system times its acceleration. And we know that for it to go in a circle, the acceleration has to be v squared over r. And in this case, the force, since the q and the v, or excuse me, the v and the b are perpendicular to each other, we just get q vb is equal to the mass times v squared over r. Now, we can also make use of the fact that v would equal 2 pi r over the period, where the period is the time it takes to go from here to back here again. That's t right there. So we could actually plug that in by canceling out this with this, and I'll get then qb is equal to m over r times 2 pi r over t. You see the r's actually cancel out in that case. And what you see that's actually kind of nice, let's cancel out these r's, is that the period t is equal to 2 pi m over qb and doesn't depend on the velocity. Because of that, a group at UC Berkeley was able to create what they called the double D's, which was literally just two big reverse D shapes. Like one was a D this way, and the other was a D the other way, but they were actually circles, and this thing won't let me draw circles like that. So poo-poo. Anyways. So I'm not going to draw it with that, but I'll say basically one D was like this and another D was like this. And you could imagine they were actually like little volume containers. So they sort of had a dimension that way, a box like that. Something like this. What could happen is you could send in a particle, say a little particle like this, it would slip right by and go right into here. And that could, for instance, be a negative particle. And the way it would do it is they would charge this plate with a positive charge. And that would also accelerate it a little bit. So the particle would come in here. And then in here, there would be a magnetic field. So this is QV is going to the right, and I want the force to go up. So I'm going to say the magnetic field would come out of the page. So let me get my green again. So right here, I got magnetic field, magnetic field, magnetic field, magnetic field, magnetic field. And we're going to say that's basically going everywhere. And it's fairly uniform. It should be really uniform, to be honest with you. And because of that, what's going to happen is it's going to cause the particle to go in a circle. So the particle will go in a circle like this. Oops. It's supposed to be a different color circle. It'll cause the particle to go in a circle like this. And of course, that circle you can see from this part, which is not where I stopped, but you can see that we had QB is equal to MV over R. So you'd say R is equal to MV over QB. So the R does depend on the velocity, but the period does not. Well, guess what? When the particle gets here, T is equal to 1/2 the period. So then what they would do is they would cause this part, this plate, this D, to become positively charged. That's going to cause the charged particle to accelerate. Well, actually, I was drawing a negative particle. So that's going to make the negative particle accelerate towards it. And then it'll come across here and another circle will happen. Then they'll switch it to a positive again. That'll speed it up a little bit more. But because none of this depends on the velocity, this frequency and period don't depend on the velocity. I should say, I can say that by this. Hold on. Frequency is equal to 1 over the period. That's going to be QB over 2 pi m. So you can see that neither depends on the velocity. So you can just keep flipping it back and forth. And every time it goes through that little gap, it's going to speed up, speed up, speed up, speed up, speed up like that. And actually, I think I did half this problem as if the particle was positive and half was negative. So don't pay too much attention to the signs and the directions, because you're going to get, you might get the wrong answer. So just think of this as a process. But either way, you now have an equation for the radius of the circle that a charged particle of mass m and charge q would experience in a magnetic field B if it had a velocity v. That's the radius, and then that's the period, and then that's the frequency. So that's now time for class to be over, and I think I've gotten you started where you can start trying to experiment with applying the equations that we gave you today, and doing your homework and examples in the book. And I will see you guys Tuesday. And like I said, you feel free to text me tomorrow, the weekend, or whatever. If I get too many, I'll just tell you I can't handle it. I'll send out an email to everybody, but I don't suspect that's going to happen, but I do want to offer that to you guys. So I hope you all do well. I hope you make a lot of good grades on your practice tests. That'll be an indicator that you're going to do well. So you're free to go, and thank you for coming. And I'll wait for the last person to leave in case anybody has any questions.
Hey, Professor, real quick, I believe we have also an online test due on Monday. I don't know if that was before you changed the date, or is that what you
Yeah,
intended to do?
that should not be the case. I did want you to have one, but I didn't want it to be due right now. So let me fix that real quick. It's supposed to be there so y'all could have more detailed studying on just those two chapters if you needed it. So that was the whole reason I put it there. Monday is November 1, right? No, Wednesday's November 1. So I might have already changed it. Oh, okay. I've got this on 30, which is Monday. This is your class. Okay, so that's wrong too. There's an online test, practice test 5, which is due November 1. That would be Wednesday, which is definitely not correct. I'm going to go ahead and change that one to, I'm going to change that to the Sunday after the 5th. I mean, after the 1st. So I'm going to change that to the 5th. I'm going to change the due date to the 5th. So that's the online test. Now I'm going to go back to the practice test and make it go up until the 31st, not Monday, because Tuesday is your exam day. So I have October 30th on there for right now. That's not correct.
All right. Well, appreciate it. Thank you.
No problem. Have a good one, Tony. Thank you, everybody. Once I get stop sharing, let's end. Bye, everybody. Bye.